So we are here today to talk about the structure of matter. So there are many different kinds of atoms that exist in the universe, but each atom, however, is made up of the same three major particles: protons, neutrons, and electrons, as you can see in this configuration here. A proton is a positively charged particle located in the nucleus of an atom. A neutron is a neutral particle located in the nucleus of an atom, and the electron is a negatively charged particle located in the region surrounding the nucleus of an atom. So the number of protons within the atom are so important it is given a special name called the atomic number, and it is found right there. An atom with one proton, for example, is called a hydrogen atom. Hydrogen atoms have an atomic number of 1, and an atom with 6 protons, as seen here, is called a carbon atom. Carbon atoms all have the atomic number of 6, and it is the number of protons that make up the atom of one element differ from the atoms of all the other elements. Neutrons are also located in the nucleus of an atom. To determine the average number of neutrons in an atom, you simply need to subtract the number of protons, the atomic number, from the atom's mass, or the atomic mass, and round it to the nearest whole number. The sum of the number of neutrons and protons is called the mass number. This value is always a whole number. For most elements, the difference between the atomic number and the mass number is the number of neutrons in the most common form of the atom. So here we find the atomic number, and this here is the atomic mass. So in order to figure out how many neutrons we have, we need to take our atomic mass minus our atomic number, and that'll give us the number of neutrons. So in the case of sulfur, we have 32.07 minus 16 equals 16.07, and if we round that, it's going to give us 16 neutrons. So the atomic number is the number of protons in the nucleus of an atom. The atomic mass is the average mass of the atoms in an element, including all isotopes, and the mass number is the total number of protons and neutrons in an atom. So recall from previous science courses the modern model of the atom. This model is has a number of features that are quite surprising. For example, the protons and neutrons make up most of the atom's mass, but these particles do not occupy much volume because they are located in a tiny space in the center called the nucleus. The electrons are particles with much less mass, but they move rapidly through the larger region surrounding the nucleus. This is why the space outside the nucleus is often described as an electron cloud, as seen here in this picture. So, comparing neutrons, protons, and electrons. So if we see here, we have the proton, okay, is located in the nucleus, and it has quite a large mass, close to that of the neutron as well, but it has a charge of +1. The neutron, again, located in the nucleus, has a similar mass to that of the proton, and it has a charge of 0. Electrons surround the nucleus, and they have a very, 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 very small mass, but a charge of -1. So the electrical characteristics of these particles explain why the fast-moving electrons are bound to the nucleus. Since oppositely charged objects are attracted to one another, the negatively charged electrons are attracted to the positively charged protons in a neutral atom. The number of protons and electrons are equal, balancing the positive charges with the negative charges. The electrical characteristics of protons and electrons can also explain why one atom will bond to another. When two atoms approach one another, the atoms are initially repelled due to the interactions between the negatively charged outer electrons. However, it is the large concentration of positively charged in each nuclei that can exert a greater attractive force on all electrons in the vicinity. So here we see we've got 3 protons, sorry, and 3 electrons So that means that this is neutral. So here we go. All matter is made up of a large number of atoms associated with one another. The protons, neutrons, and electrons that make up each atom determine how that atom bonds with other atoms. These particles also determine the physical and chemical properties of each substance. So when you are wondering why material shines, why it is soft or rigid, or why it has the ability to conduct electricity, you need to ask yourself these questions. How are the protons, neutrons, and electrons interacting within that substance? And what is the structure of the atoms within the substance? The answers to these questions will provide you with information about the properties of the atoms that make up the substance. And they will also provide you with information about how the atoms within a substance interact with each other. You can use these two insights to explain the unique properties of a substance. So to sketch a diagram of atoms, so once you have determined the number of protons, electrons, and neutrons that make up an atom, it is easy to put this information together to sketch a diagram of the atom of a particular element. This type of diagram is often used in this course is called a Bohr diagram, named after the scientist Niels Bohr. Bohr developed the idea that only a certain number of electrons were able to occupy an energy level. Electrons in an energy level closest to the nucleus have the lowest amount of energy. So this is Bohr's idea, is that you have the nucleus in the center, you have a first shell of electrons which contain 2 electrons, the second shell which contains 8, and then the third shell which contains 18 electrons. An energy level is a specific region surrounding the nucleus that is available for electrons to occupy. So, to sketch a Bohr diagram of an atom in a particular element, you need to follow these steps. So step 1, you need to use the atomic number and the atomic mass listed on the periodic table, either on those pages or in your data booklet, to determine the number of protons, electrons, and neutrons that make up an atom. Next, you draw the nucleus of the atom with the appropriate number of protons and neutrons within the nucleus. Step 3, we use dots to represent the electrons in each energy level that surrounds the nucleus. Each energy level holds a specific number of electrons. The number of electrons in a given energy level is shown by the number of elements in each period, or row, on the periodic table. So for example, the first energy level can hold 2 electrons. This is shown by the first period having only 2 elements, hydrogen and helium. The second energy level of an atom can hold 8 electrons. This is shown by the second period of the periodic table having 8 elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride, and neon. Remember, energy levels closest to the nucleus have lower energy levels and are filled first, followed by the energy levels farther from the nucleus, having higher energy levels. So for example here we have phosphorus. Okay, for phosphorus we know the number of protons is the atomic number, in this case 15. The neutrons is the mass number minus the atomic number. So in this case it is 31 minus 15. So the number of neutrons is 16. And then because this is an atom and not an ion, we know that this particular diagram should have 15 electrons. So, for a sample problem, let's sketch the Bohr diagram of the most common form of the chlorine atom. So first we need to determine the number of protons, electrons, and neutrons. So, using this information here, which is a copy of what would be in our data booklet, we can see here that the atomic number is the number of protons, which is 17. Okay? The number of electrons is equal to the number of protons because it is a neutral atom, meaning 17 electrons. The number of neutrons is the atomic mass, in this case 35.45, minus the number of protons, which in this case is 17. We are going to round that off and it becomes 18 neutrons. So next we need to draw the nucleus of the atom. The nucleus of the atom contains the protons and neutrons. Then we draw the electrons in their appropriate energy level. Chlorine has 17 electrons, so the first energy level can hold 2 electrons, as we see here, 1 and 2. leaving 15 more to place. The second energy level can only hold 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, leaving 7 more to place. The third energy level can hold 8 electrons, but there are only 7 remaining, so the final 7 will fit on the third energy level. 1, 2, 3, 4, 5, 6, and 7. But there is a more concise way to represent the final Bohr diagram, and that is in this diagram here, where we draw our nucleus in the same way, but then each energy level is shown as a line with the number of electrons available on it, with the first energy level being that closest to the nucleus, as we would draw it in the Bohr diagram. We have Lewis dot diagrams. The electron and the outermost energy level become involved in chemical interactions. Therefore, chemists are most interested in these electrons. So rather than to draw Bohr diagrams, the more efficient way to represent atoms is to use Lewis dot diagrams. A Lewis dot diagram is a representation of an atom that shows only the valence electrons, or the electrons on the outer energy level, as shown here. Oh, oh no. Well, I hope you can see it. We'll go through it together. So, for Lewis dot diagram, first we need to write out the chemical symbol. This symbol will represent the inner electrons and the nucleus. Step 2, we need to determine the number of electrons in the outermost energy level. And step 3, we use a dot to represent each electron in the outer energy level. The dots are placed on north, east, south, or west sides of the symbol. Each position has only room for 2 electrons. Double up electrons only after the other positions contain at least 1 electron. So for example, here we have chlorine, and it's got 7 valence electrons. And as you can see here, these are doubled up. Okay, and we've only got this one extra one here. So, example problem. Draw the Bohr diagram and Lewis dot diagrams for the atoms of oxygen and phosphorus. So these are best organized in a table. So we've got oxygen, okay? Our Bohr diagram here, we see we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons, but there would only be 6 in the outer valence electron level. So when we draw our Lewis dot diagram, we only have to show 6. So as it shows here, we would go 1, 2, 3, 4, 5, and 6, only doubling up once all the other 4 have been filled. Phosphorus, on the other hand, has 15 electrons, and it's only got 5 valence electrons, again showing in this configuration here. So, atomic bonding. When two atoms become close proximity to one another, the electrons are attached to both nuclei. The electrons in the outer energy level are the most significant electrons in this process. These electrons are called valence electrons. Valence electrons are those that indicate the bonding properties of an atom. The valence electron that occupies the outermost energy level of an atom. So as we can see here, as two atoms approach each other, each nucleus begins to attract the electrons of the outer atom, and they become bonded. Okay, the nucleuses do not just like smack together and form one nucleus. They still have separate nucleuses. Their electron clouds are really what is interacting. So if you, for example, look at the Lewis dot diagrams of lithium and sodium, as shown here, you will notice that their Lewis dot diagrams are very similar. Each atom has one valence electron. As a result of their similarity, these two atoms also have similar bonding properties. The same is true if you compare the Lewis dot diagrams of fluorine and chloride. In these cases, both atoms have 7 valence electrons, and as a result, their similar electron arrangement, these two elements have similar characteristics when they form bonds with other atoms. So why are these outer electrons so significant, and what characteristics determine the bonding ability of an atom and how it is related to valence electrons? To answer these questions, you need to look at the Lewis dot diagrams of the elements that generally do not react or bond. These are the noble gases. So, the Lewis dot diagrams of the noble gases. We've got helium, neon, argon, krypton, xenon, and radon. If you look at each Lewis dot diagram, you will notice that each atom all have a full outer energy level. Stable atoms, such as these, rarely form bonds and as a result of their filled electron levels. As you saw earlier, the arrangement of protons, neutrons, and electrons determines the property of an atom. So for noble gases, having their outer energy levels filled with the maximum number of electrons results in those atoms being unreactive. Atoms can attain a configuration to become more like a noble gas in one of three ways: by gaining electrons, by losing electrons, or by sharing electrons. So, gaining electrons. An atom can gain electrons to fill empty spaces in its outermost energy level. So here, I have the chlorine atom. Chlorine has one empty spot in its outer energy level. It is easier for it to gain one electron than to lose 7. Therefore, it will gain one electron. By gaining an electron, the chlorine ion has one more electron than it has protons. Therefore, it has a charge of -1. This result of the atom having more electrons than protons, the net charge of the atom changes it to a negative charge. The charge on the atom is called an ion. A negatively charged ion is called an anion. Non-metallic atoms have a tendency to become negatively charged ions, or anions. An ion is an electrically charged atom or group of atoms which can be positive or negative, where an anion is a negatively charged ion. Losing electrons. An atom can lose electrons from its outermost energy level to produce a positively charged ion. So here, for example, we have sodium. The sodium atom has one electron in its outer energy level. It is easier for the sodium atom to lose one electron than to gain 7. Therefore, it will lose one electron. By losing one electron, the sodium ion now has one more proton than it has electrons. Therefore, it has a charge of a +1. So as we can see, here is the sodium atom. Then we have the sodium ion missing its electron plus one electron here, which is free to leave. The net charge of the atom changes it to a positive charge. A positive charge is called a cation. Metallic atoms have a tendency to form cations. Cations are positively charged ions. Sharing electrons. An atom can share electrons with other atoms to produce a covalent bond. So in this case, both chlorine atoms require one electron to fill their outer energy level, but they can share electrons to produce a covalent bond, as shown here, where these electrons in the middle are shared, forming this covalent bond. So two or more non-metallic atoms tend to share electrons to complete their outer energy levels. And that is the end of our show. Thank you very much, and we will see you tomorrow.